Okay, so today we will see basic features of Euclidean spaces. Okay, so we will see that Rn is a vector space for n greater than 1, and we also see that Rn has a metric space structure. Okay, so first of all, let me uh, begin with defining what Rn is again. So as I told you yesterday that Rn is the set of all n tuples of real numbers of this form. Okay, x1 to xn. These xi come from R. These xi come from R. I runs from 1 to n. Let x be an element of Rn. So this element we call it a point of Rn. Okay, we call it a point of Rn, or sometimes we call it vector, uh, a vector in Rn. These components, these are called, xi is called the ith component of the vector x. These components are in fact scalars. Okay, we will call any real number a scalar. Any real number will be called a scalar. Just as the real numbers are represented by points on the real line, you see, this is number line, and any real number is denoted by a point. In the same manner, similarly, any x in Rn, any x which is x1 to xn in Rn represents a point in Rn. We point in Rn. These things are very simple. You all know these things. This set Rn has algebraic structure as well as metric space structure. Rn has both algebraic, we call that structure vector space structure, and metric space structure. Since it has vector space structure, so we can add any two points of Rn, or we can add any two vectors, and we can multiply by a scalar. We can multiply a vector by a scalar. Okay. So how do we define this vector addition and scalar multiplication? We define vector addition as follows. So for any two vectors, say x and y in Rn, okay, take two vectors x and y in Rn, we define vector addition by x plus y is defined like this. This is x1 y1 xn plus yn. Okay, and this is true for any x and y in Rn. Okay, this is called component wise addition. How do we define scalar multiplication? So, as I said above, any real number will be called a scalar. So here, when I say scalar multiplication, this means we will multiply real number to vectors. This we define. So for any, say, alpha in R, okay, take any scalar, and for any vector x, which is this n tuple, which is denoted by this n tuple in Rn, we define scalar multiplication like this: alpha x1 alpha xn. Okay, so with these two algebraic operations, Rn forms a vector space over R, over the field R. Rn is a vector space. You can check all the properties of vector space. These two uh, uh, these two functions, addition and scalar multiplication, they satisfy all the conditions of vector space. Okay, so Rn is a vector space over R. So to study more geometrical things, uh, we need uh, we need some extra algebraic structures. Okay, here in Rn we have inner product. We have inner products. In Rn we can define inner product. In Rn we define inner product, and inner product is uh, so inner product is uh, you have already seen inner product in your intermediate classes. It is called dot product there. Okay? So for any two vectors x and y in Rn, so this means x is x1 to xn, y is y1 yn, and we define inner product like this. So as I said, it is dot product, and you know dot product is defined like this. This inner product gives us a norm. This inner product gives us a norm on Rn. You have seen these things in your linear algebra course. I am just recalling all these things briefly. If you remember, a norm on Rn or any vector space is norm of x is nothing but this inner product, square root of inner product. Okay, or in other words, you can say norm x square is inner product x. Using this norm, we can define distance, okay, which will give a metric space structure on Rn. So norm gives metric or a distance. How do we define that metric? So for any 2 point, or vectors x and y in Rn, you know, x is this n tuple, y is this n tuple. Distance between x comma y is nothing but norm of x minus y, which is norm of x1 minus y1, norm of xn minus yn. And by this definition, now we use this definition, what we get, this is x1 minus y1, sorry, x1 minus y1, xn minus yn, comma x1 minus y1, xn minus yn, which is this x1 minus y1 square, so on xn minus yn square. I forget one thing. Here we will use square root, so we get this. So in this way, we get a distance from a given norm. Okay, this distance is called the Euclidean distance. This distance is called the Euclidean distance, or in other words, this is the Euclidean metric on Rn. Euclidean distance on Rn or Euclidean metric on Rn. This metric gives Rn a metric space structure. Once it has metric space structure, we can define other basic notions of metric space. So let us recall a few basic notions that we will use in what follows. So some basic notions. Let us start with open ball. What is an open ball in Rn? An open ball centered at a point, an open ball, an open ball centered at a point, say A, in Rn, and radius, say delta, is defined by the set all those uh, vectors in Rn, or all those points of Rn such that distance between y and a is less than delta. Okay, we will denote this set by b a delta. Okay, this is open ball. Now, this open ball is also called delta neighborhood of A. BA delta is also called delta neighborhood of A. So, in similar fashion, we can define closed ball. What is closed ball? Closed ball centered at A, radius delta is, we will denote that by BA delta bar, and it is defined by this set. dya is less than equal to delta. Okay, this is closed ball. Now, having defined these two notions, we now define open set. We will use these notions in the course. Uh, so we will use all these notions in coming lectures. Okay. So next notion is open set. What is an open set in Rn? Okay, a set G of a subset G of Rn is called an open set if for any point or for any point A of G we can find a ball centered at A which is entirely contained in G. So let me write it. If for any, so this is crucial, for any A in G there exists delta positive such that B A delta is entirely contained in G. It is like this. Let me make a figure in. So suppose we are in Rn and here is a set G. It is open if for any point, take any point A here, and we can find a ball which is centered at A and some radius, and it is entirely, this ball is entirely contained in G. So if we take this point, then we can also make a ball here. You see, a smaller ball which is uh, entirely contained in G. If this happens, we call G an open set. Okay. So in other words, we call G an open set if uh, G is neighborhood of each of its points. Okay, we are saying this B A delta uh, so B A delta L delta neighborhood of sorry delta neighborhood of A. So a subset of Rn is called a neighborhood of uh, point A if that satisfies this property. Okay, so we can in other words we can say set G of Rn is open if G is a neighborhood of each of its points. Correct? We can show that any open ball is an open set. Okay, let me write this as a result. Any open ball is an open set. It is easy to see. To prove it, what we do, we take an open ball which is centered at A. So take B A delta as A. Okay, so this is radius delta. This is point A. Now our aim is to show that this open ball is open set, means if I take any point inside this ball, say this, so suppose this is a point X inside this ball, my aim is to give you an open ball centered at X which is entirely contained in BA delta, like this. Okay, so you see, it is so we can easily prove it, and we can write a proof. So for that, what I do, I'll connect A to X, and if you extend this, this full length is delta. Okay, now you choose. Uh, Let me write. Take this ball and uh, X be any arbitrary point. Be any arbitrary point. Okay. Now let R equal to delta minus distance between A and X. This point is X. Okay. This is distance between A and X. What we now do, we take this ball BX. I can choose R, but let me take R by 2. Bx R by 2. This ball is entirely contained in BA delta. You may check this. Okay. So how do you check? You take any point from this set and show that this point belongs at. Take this and show that y belongs BA delta. Meaning, so that distance between y and a is less than delta. Okay, do this. So distance between y comma a is less than equal to distance between y and x, and distance between x comma a. Correct? You know, distance between y and x, this is less than r by 2. And what is distance between x and a? Okay, this is dxa. So from here, what you get? You get delta equal to r plus dAx. You also know this is less than r plus dxa. Okay, which is nothing but delta. You have shown this thing. This implies y belongs to BA delta, and we are done. We also define boundary of an open set, boundary of an open set or boundary of any set. Okay, we also define boundary. Boundary of a set. What is boundary of a set omega in Rn? Okay, boundary of a set omega in Rn. How do we define a boundary of a set? Boundary of a set, we will denote that set by del omega, and it is the set of all points of Rn such that every open ball around those points, uh, th those, those open balls intersect with omega as well as omega complement. Okay, this means this is all set of all those points of Rn such that these balls intersect with omega as well as they intersect with omega complement, and this is true for each ball, means this is true for all delta positive. Okay, so this is how we define boundary of omega. So one more notion that I want to recall is accumulation point of a set or limit point of a set. Limit point of a set omega Rn. Okay. So we have omega a subset of Rn. A point A in Rn is called uh, a limit point or an accumulation point of omega if every open ball around this point A contains at least one point of omega different from it. Okay, let me write it. If every open ball centered at A contains at least one point of omega other than A. Okay, so in other words, mathematically, in other words, for every epsilon positive ball centered at A with radius epsilon, intersection omega, and when we uh, subtract A, we get a non-empty intersection. This is a non-empty intersection. Any point which is not an accumulation point of omega is called isolated point of omega. Okay. A point A in omega which is not an accumulation point of omega is called an isolated point. So this is it for this lecture. In next lecture I will talk about functions of several variables. We will talk about limit of functions and continuity of functions of several variables.